the energy breaks the intermolecular bonds. So the intermolecular bonds are broken to set the molecules free to change from solid, which before were tightly packed, and then when the energy absorbed breaks or the potential energy of the substance increases, then it means the molecules are becoming free to change from solid to liquid. Then when substances change state from liquid to solid, this time around, the molecules must be brought together. Okay, must be brought together. So it means heat energy must be released, because when temperature reduces, substances contract, reduce in volume. So when we extract heat energy from the substance, the molecules will come together, okay, to form the solid. But what you have to understand is that any change of state occurs at a constant temperature, meaning it is the internal potential energy of the molecules that increases. Their kinetic energy does not change, because a change in kinetic energy reflects in temperature, and a change in potential energy reflects in change of states. Okay, let me draw the attention of the house for the last time, because the number is still not so encouraging. So every change of state occurs at a constant temperature, and whenever it happens, we said the kinetic energy of the substance does not change, but its potential energy increases. Okay, so we discussed latent heat of fusion. Latent heat of fusion, which is the energy or the thermal energy that must be absorbed or released, okay, for a substance to change states from the solid to the liquid at its melting point at a constant temperature. Now, for this quantity of heat energy that must be absorbed by a substance, we are always interested in a unit mass of the substance, because when we know the unit mass of the substance, the heat energy that can be absorbed by 1 kilogram or 1 gram mass, then when we are given any mass, we can be able to calculate for the unknown mass once we know the value of 1 kilogram mass. So that is the rationale behind specific. So last time we talked about specific latent heat of fusion. Specific latent heat of fusion. And we saw that this is the latent heat of fusion. L subscript F. And we saw that this is the quantity of heat energy that must be absorbed by 1 kilogram mass of a substance, okay, at its melting point to change state from solid to liquid at a constant temperature. Okay, the amount of heat energy that must be absorbed or released by a unit mass, which is 1 kilogram or 1 gram mass of a substance at its melting point to change state from solid to liquid at a constant temperature. So because we know the value of 1 kilogram mass, 1 kilogram mass, if I'm given any mass of the substance, maybe m kilogram mass, I can be able to calculate for any m kilogram mass, I can be able to calculate the quantity of heat energy that must be absorbed to change state from solid to liquid. So for any m kilogram mass, the quantity of heat energy that must be absorbed, we saw that is equal to that unknown mass times the value of 1 kilogram. Okay, so the difference is that this value is for 1 kilogram mass, the heat energy that must be absorbed or released. And this value represents for any unknown mass. That is why when M is equal to 1 kilogram, we have KOF being equal to LF. Okay, so this is for 1 kilogram mass or a unit mass, and then this is for any unknown mass of a substance. Okay, so that is it with latent heat of fusion. Last time we realized that the specific heat capacity of ice, the specific heat capacity of ice is 335 kilojoules per kilogram. LF of ice is 335 kilojoules per kilogram. Meaning that for ice, which is in a solid state, ice is solid, to change state from solid to liquid, okay, at its melting point, ice must absorb 335 kilojoules of heat energy, okay, in order to change state from solid to liquid at that constant temperature. Class, is that okay? So that is the meaning of the latent heat of fusion of ice. All right. So we'll be using this in our calculations. QF is equal to M times LF. SI unit of specific latent heat of fusion is equal to, we have, when we make LF the subject here, we have Q on M. So this is joule per kilogram. But because the value is mostly huge, we express it in kilo. Okay, the reason for which here we have 335 kilojoules per kilogram, meaning this is actually 335 times 10 to the power 3 joule per kilogram. So the SI unit of, so please, whenever you are given a problem, you do not overlook the prefix kilo, because it's very, very important. All right, let's move on to heat of fusion, vaporization. Heat of vaporization. Latent heat of vaporization. For vaporization, we are changing state from liquid to gaseous. So latent heat of vaporization. If latent heat of fusion is that amount of heat energy which must be absorbed or released, okay, at the melting point of the material to change state from solid to liquid at constant temperature. Then, Charlotte, what do you think is latent heat of vaporization? Charlotte, what will you say about latent heat of vaporization? Can you share your opinion with us?
Will be the amount of heat energy that will be required for the substance to change to vapor.
Come again.
It will be the amount of heat energy required for the substance to change from its state to vaporization state.
Okay, Priscilla, let's see what you also have for us.
No, sir, it's not about it's about the definition for latent heat of vaporization. Please,
Okay.
can you come over?
We are here to come to. I spoke about latent heat of fusion. We are here to come to vaporization. Or you want me to go over the fusion?
No, you started something like is the amount of heat energy,
What
which
I said was that if latent heat of fusion is that amount of heat energy that must be absorbed, okay, or released for a substance to change state at its melting point from solid to liquid at that constant temperature, then what will you say about latent heat of vaporization? So we are here to discuss what vaporization is.
Oh,
Okay.
okay.
So Charlotte has given us her view. Let me pick another from Eguya Boatma. Eguya Boatma, what do you also have to say? Can you share your view with us? What do you think is latent heat of vaporization?
It is the amount of heat energy that must be absorbed to change state from solid or liquid to gas.
Okay, I get you. Okay. All right. So you see, all contributions fantastic. But whenever you are saying this, you don't miss some important points. It said change of states occurs at a particular temperature. And when that temperature is attained, the temperature does not change. It remains constant until everything has changed to another state. So when you are saying this, you don't forget about them. And so I said, latent heat of fusion refers to that amount of heat energy that must be absorbed. For fusion to occur, the substance must absorb heat energy, okay, at its particular temperature, which is the melting point, in order to change state from solid to liquid at constant temperature. Here, I've made mention of that specific temperature, the melting point. I've also made mention of the fact that the temperature must remain constant throughout this process. So latent heat of vaporization is that amount of heat energy that must also be absorbed or released. I'll talk about the release. That must be absorbed in order to change state, okay, at the substances what vaporization, boiling point, at the materials boiling point, in order to change state from liquid to gaseous at constant temperature. Okay, so I'm repeating, the amount of heat energy that must be absorbed or released, okay, at the materials what boiling point, in order to change state from liquid to gaseous, okay, at a constant temperature. Now, in my explanation, I spoke about absorbed or released. Absorbed refers to when we are changing from liquid to gaseous. So it means that when we are changing state from liquid to gaseous, this process, the substance or the material must absorb heat energy. When we are changing state, or the same material is also changing state from gaseous back reaction, gaseous to liquid, then it must release. It must release the heat energy absorbed. So for pure substances, okay, the amount of heat energy to be absorbed, to change it from liquid to gaseous, the same amount of heat energy will be released when it is changing from gaseous back to liquid. 2, changing state from liquid to gaseous occurs at the boiling point of the substance. So water, for instance, for this to occur, it must occur at 100 degrees Celsius. Okay. When the same material is also changing state from gaseous to liquid, it would also, the change of state would also start at the same temperature, 100. Okay. All right. Now, knowing what the amount of heat energy that must be absorbed by 1 kilogram mass or a unit mass always makes the work easier. So we talk about specific latent heat of vaporization. Specific latent heat of vaporization. Vaporization, which is LV. Elra, Mazas, help us with what it means by specific latent heat of vaporization. What do you think will be the meaning of specific? I've talked about the general term latent heat of vaporization. What do you think is specific latent heat of vaporization? Elra? Oh, Elra is not here. Okay, go ahead. Maybe Elra is thinking of it. Kelvin, what do you think? Specific latent heat of vaporization. Kelvin, can you share what you think it is with us?
Just join.
A specific latent heat of vaporization.
Yeah, I think it's the specific amount of heat a substance absorbs to.
Okay. How about
He's gonna hear.
yes? Kelvin, I can hear you.
Okay, sir.
All right. Can I get any different view of specific latent heat of vaporization? Yaba, what do you also think? Final submission, then we move on.
It is the amount of heat that must be absorbed at the body's boiling point to change a unit mass from liquid to gaseous state at constant temperature.
Good. So, thank you. So here, please don't forget we are referring to a specific mass. So you don't forget to talk about a unit mass. Okay? We are referring to a specific mass, which is 1 kilogram or 1 gram mass. So in your definition, you shouldn't lose sight of 1 kilogram mass. Okay? So it is that amount of heat energy that must be absorbed, okay, or released by a substance, by a unit mass of a substance at its what boiling point, okay, to change state from the liquid to the gaseous state at constant temperature. I repeat, the specific heat capacity of a material, specific latent heat of vaporization of a material is the amount of heat energy that must be absorbed or released by a unit mass of a substance at its boiling point to change state, okay, from liquid to gaseous at a constant temperature. So this latent heat of vaporization, okay, of water. The latent heat of vaporization of water is 2,311 kilojoules per kilogram. So LV of water, 2,311 kilojoules per kilogram. What does this statement mean? What does this statement mean? That the specific latent heat of vaporization of water is 2,311. Yes, can somebody tell us what this statement actually means? Anybody before I call? Anybody? Okay, Lizzie. Lizzie, what does the statement mean? That the specific latent heat of vaporization of water is 2,311 kilojoules per kilogram. What does it mean? Lizzie, are you here? Okay, Yaba, back to you. Yaba, what do you think?
I think it means that the amount of heat that must be absorbed by 1 kilogram of water at 100 degrees is 2,311.
Okay, Yaba, you are not done. Oh. It's
2,000.
2,311 kilojoules. Okay, Herbert, I saw your hand up. What do you also think? Herbert. Okay, so it means that 1 kilogram mass of water at 100 degrees Celsius will require 2,311 kilojoules of heat energy in order to change states from liquid to gaseous.
Please, can you come again?
Yeah, okay. I'm coming in. I've been sent information. I'm coming. So it means that what it means that 1 kilogram mass of water, 1 kilogram mass of water at its boiling point or at 100 degrees Celsius, okay, must absorb 2,311 kilojoules of heat energy in order to change state from liquid to gaseous state at constant temperature. Let me write this for you. It's very, very important. So the specific latent heat of fusion of vaporization of water is 2,311 kilojoules per kilogram. This statement means that 1 kilogram mass of water at its boiling point must absorb 2,311 kilojoules of heat energy in order to change states from liquid to gaseous at a constant temperature. So that's the meaning of the statement. This statement means that 1 kilogram mass of water at its boiling point, or at 100 degrees Celsius, okay, must absorb 2,311 kilojoules of heat energy in order to change state from liquid to gaseous at a constant temperature. That's the meaning of the statement. Okay. Now the latent heat of fusion of water, we saw that is 335 kilojoules per kilogram. Fusion, that is from solid to liquid. Okay, then LF. Then vaporization, 2,311 kilojoules per kilogram. This is LV. We could see that the specific latent heat of vaporization of water is is much higher than the specific latent heat of fusion of ice. Okay, the difference is so wide. What do you think? Can somebody share with us what the reason is? Can somebody share with us what account for this wide difference between these two? Can somebody tell us? Okay, the difference is Jima, Charlotte.
Stadia, please, I'm trying.
Yes.
Okay.
I love that.
So please, I think because the fusion has got to do with from solid to liquid, the amount of heat that will be absorbed compared to that of the vaporization, which is from solid to gaseous, the
Yeah,
solid to gaseous would be high.
liquid to vaporization is liquid to gaseous.
Okay, liquid to gaseous, it would be higher because for water to vaporize, it's at 100 degrees Celsius.
Yes.
So, like, the specific
So
latent.
you are right. The
Okay.
whole reason is that you see during fusion from solid to liquid, few bonds can be broken and a change of state would occur. During fusion, solid to liquid, only few bonds, 1, 2, 3, few bonds can be broken and a change of state would occur. But vaporization, which is from liquid to gaseous, every individual bond must be broken because the molecules must space out. Okay, so every individual bond must be broken, and so it is clear that the heat energy that must be absorbed to break this bond, individual bond, will be greater than the heat energy that must be absorbed in order to break few bonds. So this is the reason why vaporization requires more heat energy than fusion. Okay, so that's thermal energy for M. So for M mass of a substance, the quantity of heat energy that will be or that must be absorbed in order to change the state from liquid to vapor is equal to QV equal to the number of mass, M mass, times the value for each kilogram mass, LV. Don't forget, any change of state occurs at a constant temperature. So the SI unit for specific latent heat of vaporization is the same as the specific latent heat of fusion, which is still joules per kilogram. But because of its huge number or value, we often express it in kilo. Okay, so this is the expression or the relation that is used to solve change of state problems or questions. Please, any question before we apply this in solving questions or problems? If you have any concern or further explanation to be given, let me know. Okay, question. Question 1. Question 1. The heat of fusion of lead, the specific heat of fusion or latent heat of fusion of lead is 25 kilojoule per kilogram. The specific heat of fusion or latent heat of fusion of lead is 25 kilojoule per kilogram, and its melting point is 328, and its melting point is 328 degrees Celsius. How much heat is liberated? How much heat is liberated as 3 kilograms of liquid lead? Okay, I will do so. How much heat is liberated as 3 kilograms of liquid lead solidifies at that temperature? So we are looking for how much heat is liberated, how much heat energy is liberated as 3 kilograms of liquid lead solidifies at 328 degrees Celsius. I'm sending the question. Okay, so I've sent the question to the platform. Let me drop another question which would go through after this one. So I've sent the second question. So the heat of fusion, specific latent heat of fusion, is okay. In the foreign books, they usually do not use specific. When they say latent heat of fusion, it actually means specific. So the specific latent heat of fusion of lead is 225 kilojoule per kilogram, and its melting point is 328 degrees Celsius. How much heat is liberated as 3 kilograms of lead solidifies at 328 degrees Celsius? Yes, I'm sure you are done. Are we done? Because this is not a difficult question. So this time, it is in liquid to solid. The lead is in the liquid state and it is being converted to the solid state, meaning we must extract or liberate heat energy from it. Okay, Herbert, what did you get?
Sir, please, I'm not yet done.
Oh, Doku, Daryl. Daryl, are you here? Adwa, share with us what you got.
Yes, I had 75
Sev-
kilojoules.
75. Adwa, 75.
Kilojoules.
Okay. And then, Ekuya Watma. Oh, Stephanie, Rachel, you are all here. Priscilla, Teresa, Yaba, what did you also make? Ekuya, what did you get?
So, dear please, I got 75 kilojoules.
Okay, so let's look at the question. How much heat energy is required to convert 5 kilogram of ice, 5 kilogram of, hey, oh, okay, I'm giving you the second question. So the heat of fusion of lead is 25, so L 25 kilojoules per kilogram. And then the mass is 3 kilograms. So that's quantity of heat energy that must be liberated, okay, would be equal to M times LF. 3 times 25 kilojoules per kilogram. So what will happen is that, look, this is kilojoules per kilogram, and the mass is 3 kilograms. So you realize that this and this will cancel out. So 75 kilojoule will be the quantity of heat energy that must be released in order to change states at that temperature. Then question two. Question two, how much heat energy is required to convert 5 kilogram of ice at 0 degrees Celsius into 5 kilogram of steam at 100 degrees Celsius? Okay, so this time, hello.
So the 3 kilogram, what did we use it for?
That's the mass, the given mass. So 3 times the latent heat of fusion of 1 kilogram mass.
Okay.
Are you okay?
Yes, please.
In question 2, we have ice at 5 degrees Celsius changing to steam. The same mass of ice is changing to steam at 100 degrees Celsius. So this time, we are changing from ice, solid to gaseous. And we are to calculate the quantity of heat energy, okay, required to change 5 kilogram of ice at 5 degrees Celsius. Sorry, at 0. At 0 degrees Celsius to 5 kilogram of steam at 100 degrees Celsius. I want you to, think through this in about 5 minutes to see what you can. Then we all solve it. So the quantity of heat energy required can be broken down into the following. we have 5 kilograms of ice at 0. 2, 5 kilograms of steam at 100. So we'll require heat. The first stage is that once the ice is at 0, we are at the freezing point or the melting point. Here, the melting point of ice. Once we are starting at 0, 0 degrees is the freezing point of water and also the melting point of ice. So the quantity of heat energy that must be absorbed in order to change state from ice, okay, ice to water. But do not forget that every change of state occurs at constant temperature. So amount of heat energy required to change state from ice at 0 to water at 0. So the first stage is that heat energy absorbed to form water at 0. Change of states. Then the second stage is that once we have formed water at 0, it must further absorb heat energy in order to raise its temperature from 0, water at 0, to water at 100 degrees Celsius. So heat energy absorbed to raise temperature from 0 degrees to 100. Now, once we are at 100, which is the boiling point of water, this is the temperature where water will begin to change state from liquid to gas. The heat energy that must be absorbed in order to change this state from water at 100 to vapor also at 100. So here, latent heat will be required here. So plus heat energy to change states to change states from water at 100 to steam at 100. These are the processes involved. Okay, so the first one is about change of state. Change of state. So Q total will be equal to M times LV. Change of state, latent heat, plus the second state is about sensible heat, any heat which will change the temperature. So this can be calculated by any change in temperature. Sensible heat is determined by M T delta T. Then the final process is also change of state. M L V. This is F. Okay, maybe the issue is that I forgot to give you these details. Hg of water and all that. But I had already given you such information. Okay, so the mass of ice, 5 kilogram of ice times. Alvin, please mute yourself. Specific latent heat of fusion of ice, 335 kilojoules per kilogram. So plus the same mass of ice would melt. So 5 kilogram mass of ice will eventually have 5 kilogram mass of water. So 5 times the specific heat capacity of water times the change in temperature. Okay, 0 to 100. So 100 minus 0. Okay, 100 minus 0 because you are learning. Then times the same mass of ice. Mass
Does it or multiplication?
and I can see mistake. The same mass of water is what is going to change to vapor. So 5 kilogram of water times the specific latent heat of vaporization of water is 2311 kilojoules per kilogram. So 2311 times 10 to the power 3. So put them together and then give me the final answer. Let's do it systematical, okay, so that we can track each stage. Let me bring calculator myself. Yes, Priscilla.
So please, why send to the power 3?
This is, I said, the specific latent heat of fusion of ice is 335 kilojoules per kilogram. Okay, kilojoules, so the kilo. I'm writing this because of the prefix kilo. Priscilla, are you okay?
Yes, sir.
So 335 times 5, which is 1675. This is 1675 times 10 to the power 3 plus 4200 times 100. Okay, times 5. This is 2100 times 10 to the power 3. Then 2311 times 5. We have 11,555 times 10 to the power 3. So in all, then it means we can factorize out 10 to the power 3 and then add 1675 by 2100 by 11,555. So 1675 times plus 2100 plus 11,555. So in all we have 15,330 times 10 to the power 3. So times 10 to the power 3 joules. So we can express the final answer as 15,330 kilojoules. 15,330 kilojoules of heat energy is required in order to change 5 kilogram of ice at 0 degrees Celsius to 100 to steam, 5 kilogram of steam at 100. Yes, Priscilla.
Okay, sir. So with the first
Step.
line,
Priscilla,
uh,
your line is breaking.
5 times 335. Okay, so I'm saying with the first line,
Yeah.
the 5 times 335 times the 10 raised to power 3 plus 5 times 4. You didn't add the 100 to it. The 100 is supposed to multiply.
I multiply 5 times 4200. Then I multiply this and left. Hold on. Let's
No,
cross.
you didn't multiply the 100 with the.
Let me cross check. So 4,200 times 5.
Sir, please you multiply.
Yeah, so 21. This is giving me 2130. Okay, yes, I did. This is giving me 2100, 3 zeros. Then times 100. So I just picked one of the zeros and then added to 100. The reason for which I wrote it as this. So Priscilla, I did that. Are you okay? So please, is there any question? So if you are given a problem, okay, this one is not a direct change of state thing. You are heating from one temperature and then to another. Okay, as you go through this process, there will be a part where there will have sensible heat, which is heat that is changing temperature, and heat energy that is also changing state. So when you are given a problem, take your time, go through it systematically, and you can figure out the same question. I want to just twist it a little bit to see what you do in calculating the heat, quantity of heat energy. This time, we are talking about ice not at 0 degrees Celsius, but ice at -5 degrees Celsius. So your question is that we have 5 kilogram mass of ice at -5 degrees Celsius. And you are expected to calculate the quantity of heat energy required to change it from ice at -5 to steam at 100 degrees Celsius. The same question. But what I'm doing is that the temperature of ice this time isn't at 0 degrees Celsius, but at -5. Calculate the amount of heat energy that will be required to change it from -5 degrees Celsius ice to 100 degrees Celsius steam at the same mass. I want to see what you do. Start with. Ice is at -5. How would you do it? Charlotte,
Yes, dear.
I'm sure you are following it now.
Yes, please.
Okay. You sent your solution. Sorry.
Eh,
Sorry.
eh,
You can't
maybe I
you can't win the prize. Are we done? Yaba,
Yes, please.
are you done?
Yes, please.
Adwa, Calvin, Teresa, hey, Kirsten, Tucci, Stephanie, Sheila, Samuela. Today people are here. I have not been seeing some of you. Okay, so we have cooling curve to also go through. So let's quickly cool this and do the curve. What would create the difference? The difference here is that we are looking for the total energy. So if ice at -5 degrees Celsius, then it means it must absorb heat energy in order to change its temperature from -5, because the moment the temperature gets to 0, change of state would begin. Okay, so here the difference will be the heat energy that must be absorbed in order to raise its temperature from -5 to 0. So if it's able to gain that external heat energy to raise its temperature from -5 to 0, then it will just join what we've done already. So the only difference is that you calculate the heat energy that must be absorbed to raise its temperature from -5 to 0. And that is sensible heat. So still the addition will be plus, let me add that to our relation before we, so the addition will just be, let me clear QF here. So the only difference is plus MC delta T. And this side will be equal to the mass 5 kilogram times 4,200. Okay. But the only bit of difference is that the specific heat capacity of ice, okay, it wouldn't be the same as the specific heat capacity of water. At -5, we have ice. So let me give you the specific heat capacity of ice. That is 2050 Okay, the specific heat capacity of ice it's not the same as, you see, ice is different from water, solid and liquid. So their specific heat capacities will change. So 5 times 2050 times the change in temperature. Okay, the final temperature is 0. The initial temperature is -5. So the change in temperature will be 0 minus -5. So this is what will add to whatever we are doing. Okay, let me bring down that down here. So the mass of ice 5 times the specific heat capacity of ice 2050 times the change in temperature 0 minus -5. So that we have 5 times 2050 times 5. That will be the difference. Please, some of these constants in exams will be given. Okay, these constants such as specific heat capacity of water, latent heat, and then of this thing will be given. It's unfortunate I did not give you, but that is the only addition or difference it will make. It is this which will add to whatever we've already had in order to change from -5 to 100 degrees Celsius steam. Please, any question? Any question? All right. Let's begin with the cooling curve. Please, what I want you to do is that note whatever we've gone through, okay? And then after, when you are free, pick the same question, try applying the understanding in solving it without looking on your notes, okay? Along the line, when you get missing, then you can refer. Is that okay? By doing that, you would master or you'll be able to apply the knowledge gained in solving problems better. Right after the class, I'll give you an example. I'll send you an example in order to try. But make sure you have well understood this one before whatever I have for you is sent. All right, so I'm cleaning the board. So over here, we are missing sensible heat and latent heat. Cooling curve. You see, whatever cooling or heating curve, whatever we've discussed, as in a substance absorbing heat energy at one temperature to another, can be plotted on a graph. And this graph is what we are describing as the cooling or heating curve. Example, if you have water, ice at maybe at -5. Okay, please let me explain this thing. You see, if you put water in a freezer and it gets to, we know that water freezes at 0 degrees Celsius. That is the freezing point of water. Please, it does not mean that when you put water in freezer and it gets to 0, everything has suddenly changed to ice. No. At 0 degrees Celsius, we have ice and then water. Even at 0, we have few ice being formed. Okay, then complete water. But what we are saying is that the change of state starts at 0. So 0, you see some ice at the surface, at a constant temperature. So as time goes on, energy is being extracted, then ice will be formed. Okay, so at a particular time, you also see complete ice being formed, meaning that change of state occurs at constant temperature. So ice starting at 0, and then complete ice being formed also at 0. Okay, when it is being heated, it will start changing from ice to liquid at 0. Take some time, maintain the temperature. So every ice has also changed to liquid. This is how change of state happens. The reason for which we say that it occurs at a constant temperature. So it does not mean that at 0, everything is ice. Take note. So the cooling curve cooling or heating curve, we are plotting a graph of temperature against heat energy or thermal energy used. So the cooling curve, the heating curve is about, it's a graph of temperature in degrees Celsius or Kelvin against heat energy. Example, water being cool. The example I just gave, water at -5 degrees Celsius. So we are starting with initial temperature of -5 per our example. This is 0. Then heating it to steam at 100. Okay. So maybe 20, 20, 40, 60, 80, 100. Now, before ice at -5 reaches 0, it must absorb heat energy to do that. So the quantity of heat energy absorbed to raise its temperature from -5 to 0 is this, Q1. Now, so this gradient represents the quantity of heat energy that is absorbed, sensible heat. Then at 0, change of state starts. It would also absorb a certain amount of heat energy to change state, and that is latent heat. So Q2. So this represents the quantity of heat energy that must be absorbed in order to change states from liquid at 0 to ice at 0. So this part of the graph gives you latent heat. Then, oh, okay. So water at 0. Oh, sorry. Ice at 0 would have to absorb heat energy in order to reach ice at 0. Okay. Then change of state from ice to water. Then water at 0 Over here, we have water at 0. It must further absorb heat energy in order to raise its temperature from 0 to 100. So that quantity of heat energy required, or that must be absorbed in order to raise its temperature let me manage the graph. So still, this section also gives us sensible heat. So this part also represents the amount of heat energy. That amount of heat energy that must be absorbed to raise the temperature in joules. Then Q3. Over here we have water at 100. Okay, we have reached the boiling point of water. So that amount of heat energy that must also be absorbed in order to change state from water at 100 to steam or vapor at 100. And this will also give us sensible heat, latent heat. This is scale 4. So latent heat is also expected here. And that ends whatever we were asked to do. This is an example of cooling curve. This is an example of cooling curve. So if you look at it, if you refer it to what we saw, the first part of that quantity of heat energy we calculated was this. Okay. Then we calculated latent heat, sensible heat, then finally latent heat. So this is an example of cooling curve. Okay. Now, things you can deduce from the cooling curve is that, one, this temperature or this point where change of state begins from liquid, okay, this is ice to liquid. Ice to liquid. You can use this to determine the melting point of ice. So this temperature gives you the melting point of ice. This, another change of state is at this point. Okay. This temperature also gives you the boiling point of water. So you can use cooling or heating curve to deduce the melting point, freezing point, and then the boiling point of substances. So in cooling or heating curve, all that we are doing is that we are plotting a graph of temperature, its change of state, or change in temperature and heat energy, which occurs along the graph. So we are plotting the temperature to that quantity of heat energy that must be absorbed, okay, throughout the phase change or the state change of the material. Please, any question before we apply this in solving problems? So over here, we will call it as heating curve, because we are heating the substance to change to steam. If it is the other way around, steam at 100 and is being cooled to ice at -5, then we'll call this cooling curve. We'll solve examples in order to be abreast with what we mean by heating and cooling curve. Let me forward a question to the group quickly so we all look at it. Rich Love, let me get your part. Rich Love, are you there? Hello, Rich Love. Please, I'm sure you are fine. If you are not clear with something, let me know before I clean it. If I need to explain an aspect to you, come again. So I quickly do that and we move on. Okay. Then let me forward the question to the group so we all try it and see what to do. Okay, so I've sent an example to the group. Let's answer a question on, try a question on heating curve instead of cooling. Hold on, I'm coming. All right, so I've sent a question to the group. Let's read the question together. So we are looking at 1 kilogram mass of a substance. 1 kilogram mass of a substance at 0 degrees Celsius is being heated to form gas at 90 degrees Celsius. Okay. So the graph represents the temperature of 1 kilogram mass of a material as heat is added. Please, I'm referring to the last graph I sent to the group. Let me indicate this one. So the graph represents the temperature of 1 kilogram mass of a material as heat is added. So the graph as referred is a graph of temperature on the vertical axis and heat energy on the horizontal axis. Okay. And the questions, please note the questions down. Note the questions down. Question 1. What is the specific heat, latent heat of fusion of the material? What is the specific latent heat of fusion of the material? That is question 1. What is the specific latent heat of fusion of the material? Then question 2. What is the latent heat of vaporization? Specific latent heat of vaporization of the material. What is the specific latent heat of vaporization of the material? Then 3. What is the specific heat capacity of the material in the liquid phase? What is the specific heat capacity of the material in the liquid phase? What is the specific heat capacity of the material in the liquid phase? Then the last question. The specific latent heat of fusion of lead is 25 kilojoules per kilogram. Oh, okay. Hold on. This is the same question we've solved. So, the question pertaining to the graph is from 1 to 3. The first question is that what is the specific latent heat of fusion of the material?
Mr. Dia,
Hello.
are you supposed to write the question?
Yes. I'm reading out to you so that you put it down too in order to solve the problem. So what is the specific latent heat of fusion of the material? And two, what is the specific latent heat of vaporization of the material? And then the final question is that what is the specific heat capacity of the material in the liquid phase? In the liquid phase. All right, let me quickly give a sketch of the question. It starts at 0, so this part will not come. Let me clear those details. So the temperature let me reduce the gradients of the graph. Here. Then another one is here. And this is at a temperature of, okay, 80. I'm just sketching the graph using the same graph I have. Then to 90. This is 90. So this, okay. Okay, so 0 to 60. 0 to 60. Then here, let me redesign the graph. Then here, this is boiling at then from there to 90. I think this is even better. Okay. So we have this part as a temperature of 10. Then heat energy of 10. Melting, this is 30. Then we have 50. 50. Then this is 100. Then finally we have 120. 120. All in kilojoules. So this is still in kilojoules. Okay. So the keynotes 60, temperature we have 60, 80, then 90. Good. So the first question, this is the heating curve. The heating curve, meaning the material is initially at 0 degrees Celsius and is heated to 90 degrees Celsius. The first question is that we are told that the mass of the material is 1 kilogram. 1 kilogram. So what is the specific latent heat of fusion of the material? Okay. What is the specific latent heat of fusion? Fusion is melting. Okay. But don't forget, over here, heat energy that must be absorbed to change temperature from 0 to 60. So over here we have sensible heat. Sensible heat. Here we have change of state occurring at 60. Okay. So over here, the substance is changing state from solid to liquid. Over here, its temperature is being raised from 0 to 60. Then we can deduce that this is the melting point of the material. The melting point of the material is 60 degrees Celsius. So this is melting. Another sensible heat. This is where the temperature of the material has been raised from 60 to 80. Okay, from 60 to 80. So liquid at 80 degrees Celsius. Over here, we have completely liquid. Liquid, change of state to liquid starts from here. And by this point, everything has changed to liquid. Okay, then the temperature of the liquid is being raised from 60 to 80. So we can deduce that this is the boiling point of the material. The boiling point of the material is 80, where the material changes states, okay, from liquid to gaseous. So this is vaporization. Vaporization. And then the temperature of the vapor is being raised from 80 to 90. So sensible heat is what is occurring here. So we are asked to determine the latent heat of fusion of the material. And that is the quantity of the specific latent heat of fusion of the material. The specific latent heat of fusion of the material. And this is that the quantity of heat energy which will change a kilogram mass of a material from solid to liquid. Okay. Fusion starts from here and ends here. So the quantity of heat energy required to do this is from 10 to 30. So the difference is 20. So it means that that quantity of heat energy that must be absorbed to change the state from solid to liquid must be 20 kilojoules. So Q being equal to M times LF. Quantity of heat energy used is 20 kilojoules. So 20 kilojoules is equal to What is the mass of the material? We were told that the mass of the material is 1 kilogram. So 1 kilogram times LF. So we have LF, specific latent heat of fusion being equal to 20 kilojoules per kilogram. So the specific latent heat of fusion of the material will be 20 kilojoules per kilogram. That is it. That is the answer for question 1. Then 2. What is the specific heat of vaporization of the material? I want you to try this. We are to determine the specific latent heat of vaporization of the material. Quantity of heat energy to change a kilogram mass of the material at its boiling point from liquid to gaseous or vapor. Try this and then just 2 minutes will do. Yes. What did you make for question 2? The specific latent heat of vaporization of the material. Yes. Yaba yanko. Ekuya buatma. Yaba. Ekuya. Kelvin. Hello, Kelvin. Oh, let me hear from some of you as to what you got. Adwa, Herbert, Charlotte, Charlotte.
Cynthia.
And what have you made for the specific latent heat of vaporization? Okay, let's go through it together. So we are looking for that quantity of heat energy required to change 1 kilogram mass of the material from liquid to vapor. Okay. I said earlier that the horizontal axis represents the quantity of heat energy. So what this graph means is that if we look at this interval, this gradient, okay, this gradient talks about the quantity of heat energy that must be absorbed to change the temperature of the substance from 0 to 60, from 0 degrees to 60. And this represents the heat energy used. So from the graph, the heat energy used to raise the temperature of the substance from 0 to 60 is 10 kilojoules. Okay, 10 kilojoules. Then the quantity of heat energy that is used to change the state of the substance from solid to liquid. This is it. At constant temperature. This is 20 kilojoules. 30 minus 10, 20. So at this point, we have everything changed to liquid. Then 20 kilojoules of heat energy is further, Priscilla.
I got 50.
We'll check. Don't worry, we'll check. Then 20 kilojoules of heat energy is also used to further raise the temperature of the substance from 60 to 80. Then at this point, we have water or liquid raised to 80 degrees Celsius. So this is the boiling point of the material. Then 50 kilojoules of heat energy is used, okay, to change state from liquid to vapor at that temperature, 80. Then afterwards, over here we have complete vapor. So the temperature of the vapor is raised from 80 to 90 using further 20 kilojoules of heat energy. So the question demands the specific latent heat of vaporization of the material or of the 1 kilogram mass of the substance. This has to do with QV. We know QV is equal to M times LV. QV is this. QV is this. That quantity of heat energy absorbed is the difference between this. So 50 kilojoules is equal to 1 kilogram mass times LV. Therefore, LV is equal to 50 kilojoules over kilogram. So it means that the specific latent heat of vaporization of the material is 50 kilojoules per kilogram. So Priscilla, you were right. Okay. So usually when you are calling out this, please do not forget about the units. Do not forget about the units. Then the last question. What is the specific heat capacity of the material in the liquid phase? What is the specific heat capacity of the material in the liquid phase? Specific heat capacity is talked about when the temperature of the material is being changed. So you must know that over here, once the talk is about specific heat capacity, it's about changing temperature, but they've been specific. What in the liquid phase? Where do we have liquid? Over here, sensible heat. We have solid. Temperature of solid is being raised. Over here, change of state from solid to liquid. So where we have complete liquid is this part. Over here, change of state start. So it means that change of state start from here. In between, we have liquid and vapor here. At this point, we have everything gaseous. So in the liquid phase refers to that gradient, sensible, where we have sensible heat and it is liquid. So the specific heat capacity Q, which is equal to MC delta T. Okay, you are looking for C. C is Q over M delta T. What is Q? Kilo is the quantity of heat energy used to raise the temperature from 60 to 80, and it is 20 kilojoules. So 20 kilojoules over 1 kilogram times what is the change in temperature? The change in temperature is from 60 to 80, so 20. 80 minus 60, 20 degrees Celsius or Kelvin. Okay. Therefore, we'll have, this is, in order not to be confused, let's change the kilo. This is joules. So instead of kilo, I'm substituting it with 10 to the power 3. So if we look at what we have, this 20 cancels this. Okay. This 20 cancels this. And what will be the results? That will be 1,000. Okay. So 1,000 joules per kilogram per Kelvin or per degree Celsius. So the specific heat capacity of the material is 1,000 joules per kilogram per Kelvin, or you can express it in kilo. Please, any question? Yes, Lizzie?
Mr. Please, where did that 20 Kelvin come from?
The change in temperature, delta T. The change in temperature is that the temperature of the substance was raised from 60 to 80. So 80 minus 60 is what gave me 20. But please do not forget that for change in temperature, a change in temperature on the Celsius scale is equal to a change in temperature on the Kelvin scale. So if on the Celsius scale, Herbert, mute yourself. If on a Celsius scale you have a change in temperature of 20 degrees Celsius, it's also equal to 20 Kelvin. Okay, because this is 1:1. 1:1. Please, Lizzie.
Yes, sir.
This is particularly to you.
Oh, thank you.
So please, is there any question? If you have any question to ask, quickly do so, because it looks as if we have 4 minutes to end today's lesson. Let me give you the other work as an assignment. The other work which I earlier posted. Okay, so your assignment is this one, the cooling one. And I'll forward the questions. Okay, let me send the questions straight away. Let me send the questions to the group straight away. The temperature of the gas is at 160 degrees and it is cooled to 0 degrees Celsius. Okay. And for cooling, there should be emission of heat energy. For cooling, you need to give out heat energy. So the horizontal axis is the heat emitted, released, the heat energy released. It is from 160 to 0. Then the horizontal axis represents the quantity of heat energy. So it is cooled from 160 to 120 using 30 kilojoules of energy. Then change of state from 120. Okay. And the energy used from 30 to 70. So 40 kilojoules of heat energy is used. Then, after change of state from gaseous state to liquid, the liquid is further heated from 120 to 60. And the heat energy used is 20. Then change of state from liquid to solid at 40 degrees Celsius. So the quantity of heat energy used is another 20 degrees, 20 Kelvin, 20 kilojoules, 20 kilojoules. Then it is further cooled from 40 degrees to 0 using an energy of 50 kilojoules. So question 1, you have to determine the melting point of the substance. The melting point of the substance. The second question is that the specific heat of the substance in the gaseous phase. The specific heat capacity. As I said, a foreign book, so they do not use the terms we often use. So the specific heat capacity of the substance in the gaseous phase. Then the specific heat of vaporization of the substance. Specific heat, they have written that as heat of vaporization. But looking at the units, it's clear it is specific. Kilojoules per kilogram. Then lastly, 89. 89, blah, 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 blah. So, we have 86 to 91. These are the questions. Please, I will expect assignment from all of you. If you have challenges, contact me backstage and I'll guide you on what to do. All right, you have another lesson. So this is where we end today's lesson. Okay, please take care of yourself and I'll see you once more tomorrow. Please, I'll be expecting your assignment today. Bye-bye to all of you.